Alright, so welcome back to particle physics and the Standard Model. This is lecture 8. Okay. So last time we looked at the combination of charge conjugation and parity, Cp, and then we saw that I stated that it is violated in the weak interactions, and then the spooky consequences of it is that time reversal is also not a good symmetry in the universe in nature, and we saw that there is something called the strong Cp problem, whereby you expect a lot of Cp violation in the strong interactions, but then you actually do not see anything. So it is kind of a reverse problem as opposed to having a lot of Cp violation in the weak interactions. And we started thinking about how experimentalists actually measured that there is Cp violation going on in the weak interactions. So that is a theme that we will be continuing on now. Okay. So we saw that the system where the Cp violation in weak interactions was detected was the Kaon system, and in particular we looked at K0, which is a d S bar state, and K0 bar, which is a d bar S, alright. And then we saw that it is linear combinations of these that we would measure depending on what we are measuring, right. Let us start thinking about what exactly we mean by this statement. First of all, since this is as I said last time, this is a strange pion, right, that goes through for all the quantum numbers except for strangeness, and in particular it is known that K0 is a pseudo scalar just like the pion. Okay. Total S is 0, total L is 0, so it is a pseudo scalar. What does that mean? It means if I apply parity on K0, it has eigenvalue -1, correct. Similarly, parity applied to K0 bar also has an eigenvalue -1. Okay. What about charge conjugation? Is K0 a charge conjugation eigenstate? Okay, obviously not, right. K0 is not K0 bar, we just saw it right here. It is not its own antiparticle, one is ds bar, other is d bar s, right. But what I can do is see what happens if I apply K0 C on these states. Obviously I am going to get this, right. So that is trivial, right, good. Now indulge me a bit, I am going to check what happens if I apply Cp together on this. Okay. So I am just going to combine this and this. Okay. So let us see if what I get if I apply Cp, multiplicative quantum number, right. All that happens is that I pick up a minus sign from P and then I flip the K0s and the K0 bars to each other, right. So Cp now on K0 bar is minus K0, very good. Okay. Now just staring at these two equations, is it possible for me to construct Cp eigenstates? Can I use some combination of K0 and K0 bar so that I can get an eigenstate of Cp? Of course you can, right. All I have to do is add them or subtract them, right, and give them equal weightage, right. In particular, if I define some K1, okay, as K0 plus K0 bar appropriately normalized, and I call K2, sorry it is not a K2 bar, my mistake, K2 as same thing with a minus sign, antisymmetric under exchange. Then what happens? Now I go back and check the Cp properties of the K0 and K0 bar. I just apply it here and I get that Cp applied on K1 gives me back K1 and Cp applied to the K2 state gives me K2 but with a minus sign. One is Cp even, another is Cp odd, correct? So, these are the Cp eigenstates. So, as you can see, as I was telling you, right, there are different combinations. If whatever, it depends on what you want to measure. If you want to measure P, these are the eigenstates. If you want to measure Cp, these are the eigenstates that you should be thinking about. Okay? Now comes some fun consequences of this. Okay? What does this mean? It means K1, right, can decay to 2 pions but cannot decay to 3 pions. Agreed? Why is that? Just look at the C and P quantum numbers. Okay? So, this one has C equals 1, P equals 1, each of the pions have that, right? Sorry, this entire state has C equals 1, P equals 1, right. So, this is the Cp of the final state here is plus 1 and the Cp of the final state here is minus 1, right. That should be easy to check, right. And similarly, K2 does not go to 2 pions but it will go to 3 pions. Same argument. So, here the Cp is minus 1, sorry, Cp is plus 1, here the Cp is minus 1, correct? Good. Now, this statement that K1 will only go to 2 pions and K2 will only go to 3 pions is true if Cp is conserved, right. Of course, in weak interactions because these are weak processes, right. So, that is the test that you can devise now to check whether Cp is conserved or not. Why? Think about it this way, okay. You can prepare a beam of, okay, prepare, so let me write that, prepare a beam of K0 eigenstates. How can you do this? Using the strong interactions, okay. So, you just crash protons and so on. So, I am just going to simply write using strong interactions you can prepare a beam of K0 which we just saw is a combination of K1 and K2, right. Okay. So, this is the eigenstate that you are preparing, okay. Then you want to see what happens to the K0, okay. What will happen is, what would you expect is that you will have lots of 2 pi that is emitted from the beam, okay, as, or let me write as decay daughters. The K0 would decay to a lot of 2 pi near the source of the beam, okay. How near? Like a centimeter from the source, because the lifetime of this decay in particular is very small, 10 power minus 11 seconds, and then if you multiply this with roughly the speed of light you get a centimeter, okay. Why is that? Because see, this is made up of K1 and K2, right, and K1, if Cp is conserved, exclusively goes to 2 pions. 2 pions means the mass of the total mass of the final state is 2 times the mass of the pions roughly, right, not accounting for relativistic energies and things like that. And when you have 3 pions, that is obviously heavier than 2 pions, correct. In other words, the energy available, the number of energy states available for the K1 to go to 2 pions is much larger then the number of energy states available for the K2 to go to 3 pions. Okay. We can now give some technical term to this. K1, so K1 has more phase space, okay, for decay to 2 pions than K2 for decay to 3 pions. Okay. If you have more phase space, obviously then K1 would decay faster than K2. If you have more phase space, the rate is higher. That should be obvious, right? And there are more allowed final states, that happens faster. The amplitude for that is bigger, right? Okay. That is the reason why if I prepare a beam of K0, I will get lots of 2 pi right near the source, because the K1 component of it starts decaying very quickly to the 2 pi's, okay. And at the same time, and I will get only 3 pi farther down the beam pipe. Basically, you know, K0s, think of them as roughly moving in a straight line, they are not, but farther down where the beam is, you will get 3 pi's coming from the K2s. How much farther down? This turns out to be an order of meters, because the K2's decay time, you know, it's 5 times 10 power minus 8 seconds. The K2 decays to the 3 pions like, you know, 300 times, or in fact 500 times slower than the K1, correct. 10 power minus 11 versus 5 times 10 power minus 8. Okay. So, that tells you that if Cp is conserved, right, then you prepare a K0 beam, you will get a lot of 2 pi's, only 2 pi's. You might get some 3 pi's also, but you will get lots of 2 pi's near the beam and only 3 pi farther away from the beam, correct. Okay, very good. At this point, let us take a very small digression to understand something about these eigenstates, okay. So, this is where I am going to ask, we saw this K1 and K2, right, these two CP eigenstates. Are these two masses, you know, the mass of K1 and the mass of K2, are they equal? Is there any reason for them to be equal? And the answer is they need not be equal. Why is that? Because if I apply a charge conjugation on K1, right, that does not give me K2, right. Let us go back to this. So, we have K1 as K0 plus K0 bar. If I apply C on that, I recover K1 only, I do not get K2, because K2 has a minus sign in it. If I apply C on K2, I get a minus K2, correct. So, K1 and K2 are not particle and antiparticle of each other, right. That means there is no reason for their masses to be equal, they are not particle and antiparticle, right. No reason for equal masses. In fact, it turns out that these two states have a small mass splitting of about, you know, 10 power 3 times 10 power minus 6 electron volts, which you should compare with compare with the mass of the Kaon itself, which is order 100 MeV, it is a few hundred MeV, okay, much smaller. Nevertheless, it is there, it is non-zero, right. So why did I get into this digression? Because this goes back to something that we discussed in the very first lecture on what is even a particle is something we were thinking about, right? And then we said particles are quantum excitations of quantum fields, and then we mentioned Fock space and so on, right? So here is yet another shade to this. A particle is not just a quantum particle is not just its identity, it's not just a photon, it's not just a species. You really have to start thinking about particles in terms of quantum states, okay? As we saw, K0 is a particle, K0 bar is a particle, and then I made some other state with it, K1 and K2. Are K1 and K2 not really particles? Is K0 only the particle? No, K1 and K2 are also particles actually. You have to think of them more in terms of quantum states. Superpositions of other states can be particles in their own context, okay? This is very much like polarizations of light. You have to think of the right polarizations as a separate species from the left polarization. You can take photons or electrons and so on, okay? It is very similar to this. Here it is this K1 and K2 business is very much like those two polarizations, right? Depending on exactly what you measure, depending on what is the operator that you are looking at, the quantum state is what you interpret as your particle, okay? So the word particle is actually sort of a confusing concept. Better to think in terms of quantum states all the time, then you won't go wrong, okay? Very good. So with that in mind, let us go back to the 2 pions and the 3 pions, right? So we saw that you wanted if Cp is conserved, you will get lots of 2 pi's near the K0 that you prepared and only 3 pi's because all the 2 pi's have decayed away. So only the K2 part is left and the K2 will decay to 3 pi's, only 3 pi's far away from the beam, correct? But that is not what was observed, okay? That is really the shock here. They did observe an order 0.001 fraction, whatever the number was. If they saw 10,000 pions, 10,000 events, then 10 events makes an order 10 power minus 3 fraction, right? An order 10 power minus 3 fraction of 2 pi was seen far from the source, and that is a telltale sign of Cp violation. Only if Cp is violated this could happen, okay? Telltale sign or a smoking gun, whatever you want to call it. Any number of repetition of the experiments, however long the experiment was run, they always kept seeing that you kept getting 2 pi's far away from the beam, okay? So Cp is not conserved in the weak interactions. So now we can do we can give one more twist to this, right? Now since Cp is not violated, better to write this K0 and K0 bar in yet another combination. So not even Cp eigenstates are really there, right? So you can write it in yet another combination. So people do write what is called the long-lived Kaon. So I am going to put the subscript L for long. K long is the K2 plus the K2 is supposed to be mostly long lived, right? It goes to 3 pions, but no, it is K2 plus a small admixture of K1. Since it is small, I am going to put an epsilon, right? And I can always normalize it correctly. And there is a short lived state. So I am going to call it K short, Ks. That would be the orthogonal combination. Again normalizing it correctly. Okay. So, now you can work with these two eigenstates, something that is long lived and something that is short lived, the one that goes far away and decays to whatever 3 pions and some 2 pions, and the one that is short lived and decays to 2 pions, okay, and a bit of 3 pions as well, right. So, if you parameterize it this way, it gives you a nice parameter epsilon to characterize CP violation in a measurable way, right. So, this epsilon is a CP violating parameter, and that number is found to be roughly 10 power minus 3. So, this gives you some intuition for how much CP is violated in the weak interactions. Okay? It is not violated by a lot, it is violated at the level of 10 power minus 3, 1 in 1000 part. Okay? The same 10 power minus 3 is what we saw here. So you know we saw here, right. So, that is what we are characterizing in the superposition also. Okay. So, this is a very curious thing, correct, because we saw that parity is maximally violated, that is in a point mirror the weak interaction completely vanished, right, and you know that is troubling, but then after a while it is digestible, at least after you added C, you know it seemed like symmetries were restored, right. But the thing with CP is that there is no such big violation, right. CP is only very tinily violated, only at the level of 1 part in 1000, right. And that is a real head scratcher. Why can't nature have been just symmetric? Why if you want to violate, go all the way and then we can think about it. But if you violate only slightly, then our sense of symmetry about the world seems to be shaken, right. So, this is something weird, and we do not have a very good answer for why it is only tinily violated. There seems to be some organizing principle, you know, even deeper down at an even more fundamental level that is giving you all this. All these peculiarities constitute the advanced flavor problem that I was talking about. Okay, these are all hints that tell us something about the underlying structure of the universe. Okay, but there are some interesting consequences of CP violation. CP violation is super important for our own existence. Okay, why is that? Because it turns out that CP violation is a basic condition to generate the matter antimatter asymmetry of the universe, which we talked about in the first lecture, correct? Biogenesis. This is one of the 3 conditions. Okay, so I will just write it, one of the 3, it is called Sakharov conditions. Turns out you need C violation, CP violation, and the all processes in the early universe to be out of equilibrium. These are the 3 conditions. We are not going to go into that here, but it is one of the 3 basic conditions that you need to create that matter antimatter. If there had been no CP violation, there matter and antimatter would have been of the same abundances, and then they would all have annihilated. There would be no galaxies to talk about and no us to think about these things, right? However, this standard model, right, does not provide enough CP violation for this, for generating the antimatter asymmetry, for the amount of antimatter asymmetry that we see. Okay, in the standard model we parameterize it by saying it's like at the level of 10 power minus 3, right? It turns out you need a lot more, actually, orders of magnitude more than this. So, standard model does not really provide it, it gives a little bit but not enough to actually fix it. So that is what makes baryogenesis a mystery. This is one of the things that makes the standard model is inadequate to explain baryogenesis. You need some more sources of CP violation, something further in the theory, something beyond the standard model is what can fix the correct CP violation amount in the universe. Okay, it could have been the strong interactions, but even the strong interactions seem to be not giving you any CP violation, although you expect a lot, right. So it's all very mysterious actually. It's all very exciting, very mysterious. Okay, and of course people have observed CP violation in B0 systems. What are B0s? They contain B quarks, mesons that contain B quarks. Okay. So B systems, D systems. Okay, what are D systems? They contain charm quark. Okay, and so on in addition to K systems. Okay, not only that, CP violation is predicted to be present in the leptonic sector also. That is among the neutrinos. Okay, we haven't made an excellent measurement of this yet, but people are getting there. It's a very hot topic in experimental neutrino physics especially, and there is no reason for why you will the leptonic sector does not have CP violation. That also has to do with there being 3 generations. The CP violation in the neutrino sector is somewhat large, but again not large enough to explain the matter antimatter asymmetry of the universe. Okay, so even if we do measure it, we haven't yet measured it properly. Even if we do measure it, it's not going to really explain the matter antimatter asymmetry of the universe, whatever it is. Okay, so this brings us to the end of serious discussions about CP violation. In the next lecture, we will see one more fun consequence of one hypothetical fun consequence of what we can do with CP violation, how to distinguish between left and right in particular, and then we will see and then we will explore the last thing about discrete symmetries, which is time reversal. How do quantum states, how do particles behave under time reversal, what respects time reversal asymmetry, how can you measure time reversal. Okay, so we will see all this in the next lecture. All right, thank you.